So this video is the optional Prelab help video for the Kirchhoff's loss experiment. It's pretty common for this experiment for you to have not taken the theory in class yet by the time you have to do the lab. That's okay. The experiment's actually designed such that you can do it without having taken this in class yet. So this video is going to be a very hand-wavy, intuitive explanation of the difference between current and voltage and how these two quantities change or don't change in a series or a parallel circuit. Some people find this sort of an explanation helpful, some people find it really confusing, so if you don't find this video helpful, that's totally okay. Hunt down your lab instructor and get them to explain it to you in person. Now to begin with, I'm going to draw an analogy. I'm going to talk about a river because we're all fairly familiar with how water behaves. So the current in a river is how many water molecules went past a certain point over a certain period of time. So how many water molecules went past this point P over a certain period of time tells you the current in a river. The current in a circuit is how many electrons went past a certain point over a certain period of time. So again, if you could count up the number of electrons that went past point P over a certain period of time, you'd know what the current in your circuit is. Now, we can't actually count up water molecules, for example. There's too many of them. So we use an equivalent unit instead. We instead measure the volume of water that went past a certain point over a certain period of time. It's just more convenient to us. Likewise, we don't actually count up individual electrons. There's too many of them. Instead, we count up the charge because every single electron has a certain charge. So if we measure the charge that went past a certain point over a certain period of time, that's an equivalent way to measure the current in a circuit. Now, something to keep in mind for both of these cases is that current is a matter of little physical bodies moving around. In the river, it's water molecules moving past. In a circuit, it is electrons flowing through a wire. So matter can't be created or destroyed. What goes in has to come out. So the water that goes into this river has to come out of the river. And the electrons that go into a wire have to come back out of the wire. Now in a circuit, the battery is always drawn with a little plus sign and a little minus sign. What do those actually mean? You can think of it as the plus sign, the plus end of the battery is like a little fountain of charge carriers. So it splurts them up and they're forced to flow around the circuit and then come back to the negative end, which is like a drain that slurps them away again. So you can think of the positive end as like being a fountain, a source of charge carriers, and the negative end as being a sink, drains them away again. Now, current is considered to go from the positive terminal, so from the fountain, around to the negative terminal. That's called the traditional direction of current flow. The reason why we make that distinction is historically they at first assumed that the charge carriers were positively charged. We now know that electrons have a negative charge. So the electrons actually go opposite to the little arrow you draw on your circuit showing current direction. The electrons go from the negative end to the positive end. But nevertheless, when you're doing calculations, the current direction that you draw in should be from the positive end around to the negative end. So that was my discussion of current. Now I'm going to talk about voltage, and I'm going to again start by talking about a river, specifically a river that flows to the top of a cliff, falls over the top edge of the cliff as a waterfall, and then flows away. So we know that the water at the top of the cliff has gravitational potential energy relative to the bottom of the cliff. So it's got a certain amount of potential energy, and when it comes down, that can be transferred into some other form of energy. So it might be kinetic energy, how fast it's going when it hits the ground. You could also stick a water wheel in here and do work. So in terms of the gravitational potential energy, though, it's just going to be equal to mgh, where m is the mass of the water, g is the acceleration due to gravity, and h is the height of the cliff. M and g are to a large extent constants, so it's useful to think of height as being a good measure of how much gravitational potential energy you have available to you. So height is proportional to the potential energy. In a circuit, for example, you've got electrons flowing through it, and they go through a resistor, and they leave again. When they go through the resistor, they lose some energy. So specifically in a resistor, it turns to heat. You could also put a motor in here and do some work. but you are losing some electric potential energy in this case. So the electric potential energy is just going to be QV, where Q is the charge on an individual electron that's going through, and V is the voltage. So voltage is proportional to potential energy in the same way that the height of the cliff was proportional to the potential energy. So you can think of voltage as being a measure of how much potential energy this circuit potentially has, those electrons. So you may have heard that when it comes to getting electrocuted, current is more dangerous than voltage. I can sort of explain why that is now. Remember that the current is little physical bodies moving around, electrons. So high current means lots of electrons flowing through your body. High voltage means lots of energy. So being electrocuted by something that's high voltage means you're going to get badly burned. But being electrocuted by something that has high current means there's a lot of electrons flowing along your nerves, and they can start flipping switches they're not supposed to. So high voltage, you're likely to get burned. High current, there's a possibility that it could stop your heart. Okay, so now I want to talk about series circuits, and a series circuit specifically is one where the end of one resistor connects on to the beginning of the next one. So they're just hooked up one after the other in series. So let's talk first, though, about this river. So you've got a river, it's flowing along, it goes over a cliff, and then it flows along again, and then it goes over another cliff and carries on away. So think about the current in the river here. How does that compare to the current up here? And the answer should be that, of course, it's exactly the same. There's nowhere that the water could escape to. It's only got one path. So all the current here should be exactly the same as the current you measure here, should be exactly the same as the current you measure here. So the current stays the same all the way through. Likewise, in a circuit, you've got one wire and one path through a resistor, and then another wire and another path through a resistor, and then a third wire. And there's nowhere else for those electrons to escape to. They've only got one path. So the current here is going to be exactly the same as the current here, and that's going to be exactly the same as the current here. So it's a variation on what goes in must come out. Those electrons can't evaporate, therefore they're always present. The current is constant throughout a series circuit like this, just like the current through one stream of a river has to stay constant everywhere. So now let's talk about voltage a little bit. The gravitational potential energy of this river, the total decrease, is just going to be mgh, and what's h going to be? It's going to be the height of this cliff plus this cliff, right? The total altitude change. Likewise, in a circuit, you're going to have a drop in potential energy here, another drop in potential energy here. What's the voltage across points A and C? It has to be the sum of the voltage drop across this first resistor plus the second resistor. So in series circuits, the voltage drop, the total voltage drop, is just the sum of all the individual voltage drops. Just like the total altitude drop of this river is just the sum of the two individual altitude drops when it went over the two cliffs. So now I'll talk about a parallel circuit, and as usual I'll start by talking about a river instead. So imagine you've got a river, it flows up to the edge of a cliff, and it splits into three separate waterfalls. It falls down over the cliff in three streams. And at the bottom of the cliff, those three waterfalls pool together, and then the river flows away. Now, we know that the current that comes out over here must be the same as the current at the top, because what went in had to come out. So all of the water that flowed in had to come back out, therefore the current down here must be equal to the current up here. However, the current in each individual stream must be less than the total current, because it's just one fraction of the total river. So some water it went in here, some went in here, some went in here. So they all have a smaller amount of water flowing through them than the total river did. However, we also know that if we add up the current from this branch and this branch and this branch, that should sum up to the total current. So what went in had to come out, and it only went through three streams. We got all that water back. So if you sum up this current plus this current plus this current, that equals the total current. Do note, however, that these three currents don't have to be the same. This could be a little trickle of a waterfall, this could be a huge torrent of a waterfall, this could be somewhere in between. They don't need to have the same current as one another, But what you do need is that the current in this one plus this one plus this one equals the total current of the river, pardon me. So now let's take a look at the circuit. So we've got a battery and it's sending charge carriers out, and they flow into 3 different paths here. But before they do that, the current right here must be equal to the current down here when those 3 paths come together, right? So what went in to those 3 branches had to come out. So the current going in has to equal the current going out. However, the current in one individual branch is going to be less than the total because it's only getting some of that total current. So there's some going in here, some going in here, some going in here. And likewise, as in the above case, if we take the current in this branch and add it to the current in this branch and add that to the current in this branch, all 3 of them sum together, that should equal the total current of the whole circuit. So what goes in went to 3 different branches, but it's still that same total. So this current plus this current plus this current equals the total. And also note that the current through these 3 branches don't have to be the same as one another. So this could be a small current, this could be a big current, this could be somewhere in between. It depends on how big the resistance values down here are. If these 3 resistors were all identical, then you'd have the same current in each branch, but that's a special case. So let's talk about voltage now, and again I'll hop up to the analogy. These 3 waterfalls all have the same height because they went over the same cliff. So they lost the same amount of gravitational potential energy just because they have the same H value, the same height value. Likewise down here, all 3 of these resistors are directly connected to the battery by these 2 wires. So all 3 of them are directly attached to that battery. Therefore, if this is a 10-volt battery, each resistor has a 10-volt voltage drop. And it doesn't matter that they've got different currents, different resistance values, they still have the same voltage because they're all attached to the same battery, just like all 3 waterfalls had the same height because they all go over the same cliff. So now we can talk a little bit about the Prelab. I'm not going to give you the answers, but I will sort of guide you through this. So here you've got a series circuit. So you know what the total voltage is, you know what the total current is. Remember, there's only one path, so what can you say about the current here relative to the total current, or the current here relative to this current? There's only one path for the electrons to go through. Also, remember that it's like a river that goes over 3 cliffs. You've got 3 potential energy drops, so what can you say about the total voltage relative to the voltage of each of these guys individually? And the second circuit they ask you about is a parallel circuit. So you've got 3 branches here. What can you say about the total current relative to the individual currents? And what can you say about each of these voltages relative to the total voltage? It's very similar to what we just discussed. And the final circuit they ask you about is one that's a lot more complicated. So you've got 2 resistors in series here, and them together are in parallel with this circuit, with this resistor. And then you've got another one over here. So you'll have to think a little carefully about this. So you can say something about what's true of the current through this one relative to the current through this one. And what can you say about the voltage drop across both of these compared to the voltage drop across this one? And how does it all, including this one, relate to the total voltage of the circuit and the total current of the circuit? So you can draw a couple of conclusions about what's going on at various points in this circuit.